Frequency is a musical property defined by how fast something vibrates. The standard measurement for frequency is hertz, which is how many times it vibrates in 1 second. Frequency determines how high or low the pitch sounds to the human ear. Amplitude is how widely an object vibrates, and it's measured in decibels. Amplitude is perceived as how intense or loud a sound is. Here's a visual aid. This is a waveform graph. The x-axis represents time and the y-axis represents the wavelength. This is a spectrogram of me playing a single note on a mellophone. The x-axis is time and the y-axis is frequency in hertz, scaled logarithmically to fit perception of pitch. Here's what it sounds like. Although the recording is of one note, there are clearly multiple tones in a pattern, as shown by the spectrogram. These multiple notes are known as overtones, and the collection is known as the harmonic series. Most objects that vibrate at a specific frequency also vibrate at whole number multiples of that frequency. For example, if such an object vibrated at 440 Hz, it would also vibrate at 880 Hz, 1320 Hz, 1760 Hz, and so on. All of these tones heard together is perceived as the sound of one note. The harmonic series is the basis of tonal harmony. In this series exist musical intervals in the form of ratios between terms. At the bottom of the series, the absolute most harmonious intervals possible appear. However, the series progresses up whole number multiples, and frequency relative to perception of pitch is logarithmic. Therefore, as the series goes upwards, the rises in frequency will start to have less effect on the perceived pitch, making each successive interval more dissonant than the last. The most common intervals found in music today are the ones found among the first 16 overtones. The harmonic series is also a model for what sounds the most in tune and pleasant. To demonstrate this, a recording of a brass chorale using approximate intervals will be played, followed by one with precise intervals. In the second recording, listen for the full sound created by the overtones of two different notes corresponding. Here's the first recording. And now the second. I will now demonstrate the concept of inharmonicity using a Native American flute, a slightly inharmonic instrument. This means that higher overtones of this instrument start to deviate notably in pitch from overtones based on whole number multiples. On this instrument in particular, the overtones start to spread sharp as it progresses up the overtone series. It is difficult to hear in the actual tone of the flute as its overtones are very weak in volume compared to its fundamental. However, I can vent air at the inverse of the whole number multiples relative to the length of the instrument to produce a note based upon the relative partial. For example, if I was to vent at half of the length of the instrument would play its second overtone. Here's the fundamental of the flute, played with all fingers down. And now the second overtone, produced by leaking air at the midpoint of the air chamber. It's not that noticeable yet, but that pitch was a little wider than an octave. I'll play this overtone again, and then I'll play the actual pitch an octave above the fundamental using the instrument's holes. Here's the third overtone. As you can probably hear, the pitch is considerably sharp now. And here's the fourth. And it's now well over a semitone sharp. For reference, here's the fundamental.